decision on whether to try again. It's right there, ready to go.
So you don't have it like we're...
Exactly. So we shut the engine down. The engine shut down. It was we were 50 psi over a certain pressure margin. As soon as the engineer got all the data out, Elon's sitting right there. The guy that basically designed all the rocket engines was sitting right there. And you figured out, well, we'll probably just have a little bit of crust buildup on our GUI system. It's called T-tap. Probably cussed it up, caused a high pressure. Raised the laser limit 50 psi. Set the limit, increased to this Iron Maiden program in California where they ran it. This whole avionics system is here. It ran perfectly. Sent the software back, loaded the software, and went after it again. Engine, same thing happened, but this time we were in the start band on that pressure limit.
Is that when I noticed, like, one time the rocket, when it took off, it did like a swirl?
No, that was a little bit, that's a little more technical about the way the cooling tubes are on each one of the nozzles, because it's kind of, nozzles get cooled just like shuttle, but the tubes are kind of at an angle. Okay. And it causes a swirl. And so they've countered that now with software and the way the roll control is, so when we come out it doesn't clock as hard.
Oh, so
I think the next design engine to the 212 is straight.
A little bit though?
Yeah, what's that?
You're still going to have the swirl a little bit?
No. The software countered it.
It'll be all fixed with the software.
Countered it with the thrust vector control.
See, that's the thing, you know, I mean, every launch we learn from. I mean,
yeah, but that was pretty wild. It was pretty cool.
Yeah. It was expected though, and it was expected. We all kind of knew it.
It was a nice launch.
And remember, there's every rocket's got 10 engines, 9 on the bottom, 1 in the upper stage, and every engine operates independently, and we can afford to lose 2 and still make it to orbit. The only rocket that was able to do that before was Saturn V.
Hey,
you want them?
Take it down aside.
Yeah, go ahead.
Hey guys, follow me and I'll get you a better view. Each one of those hold downs has 2 clamps. They're hydraulic clamps. They rotate over the pins that are on the rocket, and then the hydraulics rotates the cams back and clamps back, and that lets the pins fly out of their sockets.
Grab some video with this, please. All right. Well, now this is a good part. Not only because there's a rocket, but there's air conditioning. Well, obviously we're now in the horizontal integration hangar where the Falcon 9 spends the bulk of its life. So about 99% of its life is spent here in this air-conditioned hangar, and only does it go out to the launch pad on launch day when we essentially use these 2 20-ton cranes to lift up the whole rocket, and we drive that transporter erector that you just watched out there in. Those rails that you were walking along are right now, they're under these aluminum platforms. But we'll drive that erector in, we'll lower the rocket on, bolt it in, roll it out, and go vertical. All that takes 12 minutes to roll out. We've got some connection time to hook up the fuel and oxidizer, and then it takes another about 10 minutes to go vertical. So the idea is, you notice out at that launch pad there isn't a lot of, and I also don't have to run up and down 16 levels. I just walk in here, walk up and down. So, I mean, there's a lot to be said about this. I can have one toolbox, all the guys go work from. I don't have to have 8 different levels worth of full tools. So there's a lot to be said for horizontal processing. Now, a couple ground rules here in the hangar. You kind of got it blocked off so you can't, I don't think you can get into a position where you get in trouble. For ITAR, so this is the trafficking in arms, we can't take shots looking up the nozzle, so you can get side shots from here, but nothing, I don't need anybody reaching over and doing this, I can't look up that way. And on the front end, we can't have pictures, you can look, but you can't take pictures into the mouth of the interstage, so when we get up there, I'll point that out. So, real quickly, let me point out a couple of the key attributes of the Falcon 9. So, as its name indicates, the Falcon 9 is named that way because it's got 9 Merlin engines. We started with a Falcon 1. Our founder, Elon Musk, got the idea that he wanted to build a rocket to help get a payload to Mars initially. We started with a Falcon 1, which was a single Merlin engine on a small tank. We've now scaled that single Merlin engine up to a 9-engine Falcon 9. So you got the 9 engines, you got a 12-foot diameter tank. It's about 112 foot long total. This booster is about the same capability-wise as an Atlas V with no solid rockets. So we're in about we can fill about the lower half of the market when it comes to launch. So, one of the things that makes the Falcon 9 a player these days is the fact that we kind of lean on 3 main principles: safe, reliable, and affordable. So, if it's affordable but not safe or reliable, nobody wants to buy your gadget, right? So you get safe and reliable are the key. So some of the things we do to make it reliable are, and rockets kind of have 3 main things that can go wrong during launch. The engines can go bad, your stages can fail to separate properly, so the first or second stage hang up, or your avionics, usually less so avionics can fail, so it can, computer goes bad. So one of the things we did with the clean sheet design of the Falcon 9 is we made this engine out capable. So we can lose an engine during liftoff or all the way through orbit and still make orbit. So that's a reliability factor. Each of these Merlins puts out about 100 to 120,000 pounds of thrust, depending on how they're tuned. So you get about 1 million pounds of thrust from the first stage and another 100 to 125,000 from the second stage. So what you get is about 10,000 pounds to geotransfer orbit, that's 23,000 miles, and about 23,000 pounds to low Earth orbit. So think 300 kilometers, that's the space station orbit. So that's the capability. Now on the affordability front, we're the only guys that advertise their price on the internet. So you go to SpaceX.com, there's the price. Elon got his money in PayPal, so I think soon there will be a buy now button. Click and charge $53 million to your PayPal account. But I mean that's important because if you look, one of the problems with the U.S. losing its position in the launch business is not so much that we've lost it internally, but we're losing business overseas. So we're starting to win business that is traditionally, U.S. satellite companies are paying to go to Russia, China, India, French Guiana with the Europeans to launch their satellites. They would prefer to launch it here. So the fact that we've got a 100% U.S. built rocket and it's about 1/3 to 1/5 the price of the competition on either side of this with Atlas and Delta. If you can get it safe and reliable, then it becomes very appealing. So we've had 2 successful launches, 2 for 2 with the Falcon 9. This booster is going to launch in somewhere in the fall, October, November is what I'm anticipating, depending on how the Dragon comes together and the NASA comes together. But this idea that you can be safe, reliable, and affordable is what's going to change that's really what we're trying to get at. With the shuttle flying out, people kind of tend to think, wow, the space program is evaporating. Not really. What we're trying to do is retool it so that something safe, reliable, and affordable can do kind of the mundane. And, taking stuff to space station will never be mundane. But that's not where NASA needs to spend their big money. They should be exploring asteroids and going to Mars. Let's let them spend the money on that, and we'll just take care of supplying low Earth orbit. And eventually, this booster was built to fly astronauts. So all the factors of safety are the manned factors of safety. So when you're building a rocket, the safety factor for a manned version is 1.4, so you have to build it 40% heftier than you need to. And for an unmanned, it's 1.25. So we built everything to 1.4. Every Dragon capsule has 2 windows. Guarantee there are no windows required for cargo. They don't care. So we built this all along to fly crew members. So we're one of 4 companies to be awarded a commercial crew contract from NASA to explore how you rate your booster and your capsule for manned flight. So our big thing with that will be to put a launch abort or launch escape system on the Dragon capsule so they can escape in case the rocket veers off course. So, a couple quick attributes of the rocket engines themselves. So it's a fairly simple liquid oxygen RP1 engine. Single turbo pump feeds both commodities into the thrust chamber. the igniter is actually on the pad. It's called T-tab. It's a pyrochloric that when it hits air, it lights. So you have fuel, oxygen, and now a flame, you get ignition. So this is your nozzle. This is a gas generator cycle engine. So we put about 98% of the thrust out the big nozzle, and about 2% is bled off into this gas generator. And that basically just keeps the turbo pump spinning at really high speed, so as those commodities come in. You can see two of the hold downs. So you saw the big hold downs out there, the hydraulic clamps. That's what they'll clamp onto. You also probably saw liquid oxygen and fuel pipes coming in from the side to the base of the pad. When the transporter is mated to the booster, it's got male ends, and these are female quick disconnects. So the transporter will drive in here, and RP1, nitrogen, helium, and other gases will all plug in here. So when the thing goes vertical, you got the male and the female sitting on. So when the rocket can fill from the bottom, so these are the pipes that will actually fill. Fuel on this side, liquid oxygen is up top. It will tank the whole booster through these connects. And then when the rocket lifts off, there's no fancy umbilical or quick disconnect or anything. It just lifts off, the little plate closes, and it flies away from the interface. So very simple. What you'll notice about the Falcon 9 is on the grand scale, it's a very simple rocket. Simplicity is life. We don't try and use fancy computer algorithms to squeeze the last 10% of performance out. Frankly, probably more like the Russians in this sense. We build them big, we fire them. These engines, you can see they look a little dirty. It's because they were fired in Texas for over 400 seconds total time. Tested. And we'll fire them again a couple days before launch. We'll roll it out there, fuel it up, and light it on the pad for about 5 seconds, just to make sure one last time that everything's working. And I mean, we're one of the few guys that do what I call the inter-runway check. So we'll, just like the pilot at the airport, when you get on an airplane, he stamps his foot on the brake, he goes full throttle, and you sit there on the runway for just a split second while and then he lets go and you start that. We do the same thing. Those hydraulic clamps hold the rocket down for about 4 seconds while it's straining to launch. And only when the flight computer notices that there's over 1,000 launch commit criteria, that all those are good, does it send a command to those clamps that were out there to open up and fall back sliders for the rocket. Any questions down on this end? If not, we'll start walking up to the front end. Yes, sir.
Did I understand you to say that the igniters are on the ground?
Right. For the first stage. For the second stage, we have a canister on.
That was going to be my question.
Yeah. Hard to light those from the ground.
What about reusability? Where does that fit in the skating art?
We do. I mean, Elon's very interested in reusability. Yeah. I think reusability is part of our block 2. We tried the first 2 launches to recover the booster, and it's not built for it. It wasn't stiff enough. So we had to make some mods. Those are being rolled into the next 2.
So it's nothing.
No, probably 6th or 7th launch perhaps. This is going to be number 3. So. Now the tank itself is built of aluminum lithium. Yeah, I would ask you not to put your hand on it, but you can see it's pretty stiff. It's aluminum lithium, but the booster is 85% built in house. So we start with blanks, flat pieces, roll them in the barrels, and roll the barrels for the tank. Switch and stir welding, all that. It's covered. It's got cork on it now, and that's for heating as we go through. And this is a common tank with fuel and oxidizer. So fuel goes up to about right here. That would be fuel. Then there's a common dome in here that separates this into 2 halves. From here forward, liquid oxygen. So you have about 1/3 fuel, 2/3 oxidizer. Yeah, basically close out aerodynamics. Raceway here, one on the other side as well. Carries a single command from the flight computer, which flies on the front of the cycle, back to the controllers, the nozzles. All 9 engines are controlled separately, because if you lose one, the other 8 have to figure out how to accommodate the loss. most satellite customers want some kind of a backup plan if you can't launch it. So either our thing is we don't get paid until we launch, so there's an incentive on our side.
Sarah, how far back do you want them to need?
No, we're fine. Yeah, you can't. I'd actually not go past the tape. You can go if you want. You can go in here and shot up or back. Just be careful. The only real hazard in this hangar is that your feet don't trip over these rails or these grounding straps. But
do not touch anything.
Don't touch the composite. Don't stick hands in the. You can see a shot like that. Of course you can rotate. You'll see at this interface we go from the aluminum lithium first stage tank to the inner stage. The inner stage is made of it's composite. I'm sorry. But the inner stage performs two main roles. One, it houses the second stage nozzle. So just the second stage flies the Merlin engine, much like that engine up front. The difference is the nozzle. The nozzle is in that aluminum box right there. So it fills almost this whole volume of interstage. So it's 96 inches long and about yay big around. And that's because the second stage has to fire in 0G in outer space, and the plume expands differently than it does in the atmosphere. For the most efficient burn, you use a large expansion. You'll also notice the separation system. So you see these metallic things located about every 20 degrees around the room. Most rockets use explosive bolts or bolt cutters or explosive clamps to separate stages, but the problem with that, one, you have explosives, and two, when they go off, it puts a jolt into the capsule or the satellite, and most of those dainty electronics don't like jolts if they can avoid it. So what we've done is built a pneumatic system, which is fairly unique to SpaceX. We use a ball and piston system so that each one of these things is like a socket, and the second stage would be a ball. So they would close around, and when it's ready to separate, the computer says open up the sockets and then extend the pistons. These pistons would then drive out. And so instead of just get a nice push the first stage away. This falls away and tumbles off. You wait a few seconds and then you light the second stage. So this is a two-stage to orbit. We light the first stage, it burns for 3 minutes. We separate. The second stage burns for 5 minutes and you're in low Earth orbit. So that's another one of those reliability features. The fewer staging events you have to do to get to orbit, the better, because those are problems. Right. Well, so what will happen? This is the first stage of the interstage. Tomorrow, the second stage arrives from Texas after being fired on the test stand. We'll go in those two carts just like this. We'll be able to roll it in and out, rotate it. When it's finished, we'll put the nozzle on, and all that will set in here and make. Then the Dragon capsule will come probably a few weeks after that. It'll go on 2 more carts. And so you'll have first stage, interstage, second stage, Dragon. Crew? The crew? No, the crew would go into Dragon capsule, which isn't here yet. And right now, we're set up to fly cargo to the space station, but crew, not yet. We designed the capsule for crew. We're not flying crew in Dragon.
How are you going to handle the clean room kind of atmosphere, if that's not the wrong word?
Yeah.
I mean, if you look at the ATV's big road recently, I mean, everybody's in a bunny suit. The whole thing is,
yeah.
Anally.
We'll actually do.
Are you guys going to have to do the same thing?
Yeah, we will do. Matter of fact, we'll set up laminar flow sort of temporary cleaner. This is one of them right here. And we'll go in and process cargo, and we'll roll that up to the hatch of the Dragon. Close that down, guys. We'll be in bunny suits, so we will be. It's not what they call 100,000 class clean, which is what you do for satellites, but it is more than us walking around. So there is a higher clean.
Before it's human rated, so before that first cruise flight, and will that be orbital?
Yeah, it'll be orbital. Two main things. This is what we're developing under NASA's Commercial Crew Development Program. We're one of 4 contractors under CCDEV Commercial Crew Development 2. But the big things are, first, the launch escape system. So that's the system that would, you know, if the rocket was breaking up, would pull the capsule away and fly the crew off and land them safely. So that's the big thing. We're building in a rocket-assisted internal to the Dragon so that it just doesn't require a puller to pull it off, it pushes off. And then the other thing is the crew accommodations themselves. So this is the life support, the seats, that kind of thing. So the Dragon is essentially ready now for that environment. It doesn't have a launch escape system, and it's configured to seat 7 design, but we don't have the physical life support stuff built in. So that's
the first capsule pressurized.
We did, yeah. It's pretty benign.
Do we have living organisms on board?
No, we didn't. Cheese. A block of cheese here.
And you'd like your own astronaut for the...
It could, you know, that could go anyways. Yeah, we have 2 astronauts on our company staff that are big into the crew part of things. We may fly SpaceX test pilots first. We may fly a combination of astronauts and test pilots. We may fly just NASA. I don't know.
And are people wanting to be the first to do that?
Oh, there's a long list of people that are ready to believe. Yeah. In the company, I think there's about 300 or 400.
So your setup process is one at a time. And you're looking to do 12 to 15 a year. So you're looking to roll them in and roll them out on about every 3 weeks.
Yeah, about every 23 days. And the way we do it, this is where final assembly is done. Now we have a hangar off-site that's capable of holding 2 more. That while this one's being ready for launch, those are being prepped. So as soon as this one goes, they would roll out.
What sort of prep would you be doing over there?
Pretty much the same thing we do here today, but we didn't have that in the past. This is the only facility.
So basically, you could get everything prepped and made them here.
Right. So we bring them out. They would already be pressure tested, leak checked, avionics would be ready. So you're really then just doing final integration, so connecting everything up.
They come on rail cars, do they? Is that
no, they come over the road on truck.
How long would it take to integrate? How long would it take to integrate in that scenario? Assuming everything's ready.
Yeah, if everything's ready, you're talking somewhere on the order of 20 days. You know, and that's build it, roll out, and fuel it, roll it back, make sure everything's good. We do a hot fire on the pad, so we light the engines for 5 seconds, a couple days prior to launch. So you're talking.
You're not actually going to have much things like you can check then.
You get 3 days. Yeah, we think that you get about 23 days between.
Yeah, 20 days.
Yeah. You're right.
Like this sun here, burn up
yeah, this would fall off and re-enter into the atmosphere, burn up.
any part at all that can be used beside the capsule.
Yeah, ultimately, the first stage, second stage, and capsule are all meant to be used.
So that's really the
We're
only
not there yet. Even the first stage, we want to recover it, reuse those engines, reuse the tanks. It's a challenge. Yes. I mean, the business plan is built on big step to getting launch affordable.
Okay, we're done. Are we going back to the bus?
You're going to the bus and then you're going to the LCC.
Okay, guys, let's go back to the bus. Yes.